Hi, my name is Jamie Kinney, and I'm a solution architect for Amazon Web Services. I'm part of the global public sector organization here at AWS, and my focus is on high-performance computing and big data applications of the cloud. The organizations that I typically work with are research institutions, Department of Energy labs, space agencies, including NASA, but also others around the world. And really have the fortune of being able to talk to many folks like yourself. So I first want to start by saying thank you for taking the time to attend this session. What I'd like to do over the next hour and 15 minutes is provide an overview of how scientists are using the Amazon Web Services cloud, talk a bit about the capabilities of Amazon Web Services that are relevant to the scientific community, provide a few examples of how researchers are using the cloud today, and leave some time for questions at the end of the session. Maybe to first kick things off, I'd like to talk first about why we're seeing a tremendous influx of researchers beginning to use the cloud. And it was actually Kate Key who first gave me the idea of this concept of time to science. Today there's a challenge in that we have large supercomputing centers that are distributed around the world, and they're built with tremendous capacity, fantastic interconnects, and queuing systems that enable researchers to define a job that describes what they'd like to accomplish, submit that job, and then sometime later get the results back. And while this approach works well for many, many workloads, it's very common these days to find supercomputing facilities that are running low on capacity or not able to deliver the specific type of cluster that's appropriate for a given workload. For example, many supercomputing facilities will have the predefined percentage of servers that have standard CPUs but no GPUs within them, or might be built on a certain processor architecture that may or may not include things like AVX extensions that are found in the Intel Sandy Bridge processors. And so as a result, applications are being developed to kind of run on potentially a least common denominator platform. The other thing that happens is that not all jobs are equal. Many jobs will require large numbers of servers, have a priority that need to be completed in a certain fashion, and with shared resources, that always results in queuing. And so the impact of that is that researchers may not be able to ask all of the questions that they'd like to. They might have to wait longer than anticipated to model the latest outbreak of H1N1, or may not be able to analyze all of the data sets that they have access to related to sea surface temperature and increasing levels of carbon dioxide in the air column. Or they might not be able to scan as much data coming from infrared satellites and space telescopes, and thus won't find as many extrasolar planets. And so what we want to do at AWS, at Amazon Web Services, is to provide researchers with the tools that they need to be able to deliver high-performance computing clusters whenever needed with exactly the configurations that's needed for the given job at the lowest cost possible as well. And so the first element that's really important for cloud consumption of high-performance computing is the ability to have on-demand access to the infrastructure. We have, within Amazon Web Services, data centers located all over the world. I'll talk a bit about those precise locations, but anybody can show up and literally within a few minutes create an account and provision a large multi-teraflop supercomputer on AWS built on our commodity infrastructure. Secondly, scientific workloads not only require large amounts of compute, but typically involve very large data sets. So it's important to be able to not only easily move data sets back and forth, and Amazon's network capacity helps us out, as do some of the file transfer tools that we make available, and others have developed on top of our platform that are available. But it's also important to be able to reduce the cost of long-term data set storage. So if you're keeping terabytes or even petabytes of data online, you need to be able to store that in a way that is in line with the value that's derived from having those data sets stored online. And so one of the benefits that we see is the ability to very easily share a common data set with others, with the cloud becoming a meet-me room, if you will, allowing many researchers to access the same data set instead of having to copy it to 20 or 100 different locations and everybody working with their own cache of that data set. And finally, the reproducibility of results in the programmable infrastructure. I want to talk about that a little bit. So all of the Amazon Web Services capabilities are Elastic Compute Cloud for server virtualization, storage APIs, dynamic Hadoop clusters. All of these are available not only through a web console, which I'll show you over the course of the next hour or so, but we also have command line APIs and web services APIs. So literally with a click of a mouse or with a shell script that could even be scheduled and further automated, you could produce a cluster, submit your job to that cluster that you've created that precisely meets your needs, generate a result set that's stored in a cloud, potentially transferred elsewhere outside of the cloud, and turn off that infrastructure. And you'll only be using what you need while you need it, and you don't have to go through many manual steps of actually configuring that cluster. So that the programmable infrastructure opens up a world of possibilities.